So in the last week, we discussed what is meant by the rank of a matrix and the determinant of a matrix, and also saw some of its nice properties. We also discussed a particularly nice factorization of a given matrix into, say, a product of three other matrices, where the first and the third one were product of elementary matrices, and the middle one, or the second one, was a block matrix with the first block being the identity and the remaining blocks being the zero matrices. This factorization was particularly useful in calculating the rank and many times the determinant of our given matrix. However, when it comes to looking at the powers of our given matrix, it's not useful to have this kind of a factorization, because there are elementary matrices involved in that, and it's quite bothersome to deal with the powers of those elementary matrices as well. So to tackle this problem, or to address the powers, there is a different factorization, more useful factorization in this case. It's called the diagonalization. So in this week, we will discuss what is meant by the eigenvalue, eigenvectors, and of a given linear transformation, and also diagonalizability. But before we come to all that, let's have a brief interlude where we discuss and recall some nice properties of the diagonal matrices. So let's begin by recalling what a diagonal matrix is. So recall that a matrix A equal to Aij is a diagonal matrix if every entry which is not in the diagonal is necessarily 0. If every off diagonal entry is 0. i.e. Aij is equal to 0 for I not equal to j. So that means A will have a particularly nice form. It will be something of this type: A110000 0, A22 0 dot 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 0 0 0 ANN. So every entry which is not in the diagonal is 0. Could happen that the entries in the diagonal also could have certain 0 entries. So for example, 0 matrix is a diagonal matrix. It's not demanded that the diagonal should be non-zero. The only thing that is being demanded is that the off diagonal entries are 0. So we shall denote by diag the short form expression for this. So let diag A1 to AN denote the matrix which is given by, let's see, A1 0 dot 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 0 0 A2 0 dot 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 0. So we can capture just the diagonals and diagonal entries and abbreviate the expression as diag of A1 to AN. So in particular, if diag of say 1 2 3 is going to be a 3 cross 3 matrix, which will be 1 0 0 0 2 0 0 0 3. Okay, so let's look at some operations with diagonal matrices. So consider two diagonal matrices. Let's look at, say, A1 0 0 0 A2 0 so on, and let's add it to another diagonal matrix. So this is going to be B1 0 0 This will give us by the very definition of matrix addition, a1 plus b1 0 0 0, a2 plus b2 0 dot 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 0, an plus bn. So if I am to use the notation that we have just introduced, diag of a1 to an plus diag of b1 to bn is equal to diag of a1 plus b1 dot 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 an plus bn. So the matrix addition is particularly nice. So check for a scalar. So let me leave it now as an exercise. For a scalar c times the diagonal of a1 to an will be equal to the diagonal of ca1 up to can. So it's not just the matrix addition which behaves well, the scalar multiplication is also particularly nice. In fact, not just these two operations. If you take two diagonal matrices and multiply them, that also is particularly well behaved in the expressions that we have developed. For example, if you look at diagonal matrix, when multiplied to another diagonal matrix, I will leave it to you to check that this is going to be just the component wise product here. So if I have to write it again in the above short notation, this will be a1 to an times the diagonal matrix with entries b1 to bn will just be equal to the diagonal matrix with entries a1 b1 up to an bn, which is good because if you look at the diagonal matrix of say 1 2 3 earlier and raise it to a power n, this is just going to be equal to the corresponding 1 to the power n, 2 to the power n and 3 to the power n by what we have just noted. So in particular this is true for any n cross n matrix. So diagonal of a1 a2 up to diagonal of a1 to an, if you multiply this matrix with itself n times, this will just give us a1 to the power n, okay, it's too many n's lurking around, so let me just make it m. So this will just be m and this will just be m. So that's good. Now let's look at what happens when we look at polynomial expressions of a diagonal matrix. So let's look at it with an example. Let p of x be something like say x to the power 3 plus 2x plus 1, or maybe not 1, let's call it 3. Then p of a is defined as, for any matrix, any square matrix A, p of a is defined as a cube plus 2 times a plus 3 times the identity matrix, right. So where identity matrix is of size n, where n is the size of our matrix A. So if A is a matrix of the type say diagonal of say a1, a2, a3, let's just maybe an, let's look at a diagonal matrix of size n. Then what is going to be a to the power 3? Then I would say that the expression for p of a will be diagonal of a1 to the power 3, a2 to the power 3, an to the power 3 plus 2 times. So I'll just pull in the 2 times diagonal here to write it like this. Diagonal of 2a1 2an plus the diagonal consisting of 3 all 3's, right? And this is going to be diagonal of a1 cube plus 2a1 plus 3 an cube plus 2an plus 3 by whatever we have just seen, and this is precisely p of a1 up to p of an. So the polynomial expression of a diagonal matrix will give us a matrix which is a diagonal matrix again, whose entries are corresponding polynomial expressions of the diagonal entries from A. So again, with respect to polynomial expressions, evaluation P of A will be very easily done with diagonal matrices as compared to normal matrices. If you sit down with a normal matrix A and start looking at polynomial expressions, then forget polynomial expressions and focus on simple powers. Very soon it starts becoming quite complicated, but that's not the case here. That is what was observed. Okay. So another proposition to note, maybe lemma, is that if you recall the factorization that was being referred to in the beginning of this video, we could write any matrix as the product of 3 or okay, let's forget the factorization. If you go back to the previous week, we had seen one of the results which said that the rank of a matrix is equal to the number of non-zero rows in the row echelon form, and here that manifests in telling that the rank of our diagonal matrix is just equal to the number of the non-zero entries. So let A be a diagonal matrix. So let me refer you to the last week's lectures to conclude that the rank of A is equal to the number of its non-zero entries, Okay, so now let's look at the linear transformation corresponding to a given matrix. So let A be a diagonal matrix. So let A equal to, say, diag of A1 to AN be a diagonal matrix. So we would like to see, see the impact of that on the corresponding linear transformation L subscript A. So consider the linear transformation L subscript A, and let's see what the action of LA on typical element of Rn is going to be. Then LA of x will just be LA of v for some vector v in Rn to R in Rn would be the following. LA of v will just be equal to A1 0 to 0 0 A2 AN, and this will be matrix multiplied to x1 to xn, where x1 to xn is the column vector corresponding to v with respect to the standard basis. And this, if you observe, this is just A1 x1, A2 x2, AN xn. So if you notice carefully, what it does is that it dilates the first coordinate by A1, it dilates the second coordinate by A2, and so on, dilates the nth coordinate by an. So in particular, if you look at the impact of LA on the standard basis, let's see. So let beta equal to E1 to En be the standard basis of Rn. Then LA of E1 by what we just noted will just turn out to be equal to A1 times E1. LA times E2 is what is called as A2 times E2. LA times En is equal to An times En. So in this setting, AIs are what are called as eigenvalues and EIs are what are called as eigenvectors. So this is one of the first examples of eigenvalues and eigenvectors which we have not yet defined, which will be the content of your next video.